You've learned different reaction types: acid, base, substitution, elimination, and addition, and now you can identify structural features of different functional groups to predict how a reaction occurs. So let's apply your knowledge of reaction types and structural features to synthesize a target compound from a starting material. So you're familiar with the structural features of each functional group, and those structural features tell us how to convert one functional group to another. So it's been quite a journey learning all these organic chemical reactions, but remember that identifying the structural features helps us predict how a reaction occurs. So let's put your knowledge of organic reactions to do organic synthesis. So we will look at 4 organic synthesis strategies to convert one functional group to another, move a functional group from one carbon to an adjacent carbon, make a carbon-carbon bond to make a bigger molecule from a smaller molecule, or break a carbon-carbon bond to make a smaller molecule from a bigger molecule. Structural features such as a carbon-carbon pi bond, alpha carbon, leaving group, and carbonyl carbon give us information about the atom or bond at which a reaction occurs, as well as the reaction type, and that tells us how to make a compound. This table relates the structural features to the reaction type to the product of each reaction. So stop the video and review this table, and this will help us in synthesis. Organic chemistry textbooks say to work synthesis problems backwards from the target compound to an intermediate to the starting material. However, organic chemistry students find this very hard to do. One thing to remember is organic reactions are reversible. For example, let's look at ethanol. We looked at how ethanol reacts, and then you can look backwards. How do you prepare ethanol? Again, let's look at the structural features in ethanol. Ethanol has an alpha carbon and leaving group. That means that it can undergo a substitution reaction. So ethanol can be converted to ethyl bromide, and then ethyl bromide can be used to prepare ethanol. So stop the video and look at the other reactions that ethanol undergoes and the reverse reactions to make ethanol. So here are the reaction types. One organic synthesis strategy to convert one functional group to another. Since ethanol has an alpha carbon and leaving group, we can use a substitution reaction to convert an alcohol group to an alkyl halide group. Acetic acid has a carbonyl carbon and a leaving group, so we can do a nucleophilic acyl substitution reaction to convert the acid group to an ester group. Ethanol also has a carbon-oxygen single bond, so we can do an oxidation reaction to convert the alcohol group to an acid group. So let's do an example. You want to make a new cleaning solvent, Omnia, so stop the video and propose an efficient synthesis of Omnia from this compound. Note that you want to convert the acid group to an ester group, so you can do this by a nucleophilic acyl substitution reaction. Another organic synthesis strategy is to move a function group from one carbon to an adjacent carbon. For example, how would you synthesize 2-bromopropane from 1-bromopropane? So stop the video, identify the structural features in these two compounds, and propose a synthesis. So a substitution reaction will work if we want to convert one function group to another function group, but we can try an elimination reaction to make a pi bond and then do an addition reaction to put the Br in a different position. Let's do another one. So let's synthesize 1-methylcyclohexene from 3-methylcyclohexene. So identify the structural features in the target compound and starting material and propose a synthesis. So to move the pi bond over one carbon, we can do an addition reaction. Note that that intermediate has a leaving group, an alpha carbon, and an H and a beta carbon, so we can do an elimination reaction to make a carbon-carbon pi bond.